Okay, so we'll talk about source drain resistance. Um, so basically, we always assume that your source drain is very highly doped, so it doesn't provide any resistance to the current flow, right? But if you look at, let's see, right? So if you look at your device, right? So this is a cross section of a typical device. So we're just discussing, like we have extension. So this part is your extension. So I have a extension part, right? And extensions are there just to reduce the short channel effect. Then I have my source drain part, right? Right. So I have my extension part and I have my source drain part here, right? Okay. So so basically, this extension, let me put together. So let's say this has a junction depth xj1, and your source drain junction depth is xj2, right? And we have also seen the CMOS process flow. We know how to fabricate that. And let's say the distance of the extension is s, right? So s is determined by the spacer, right? So how do you create this extension? Like what is the spacing between extension and source and drain? So the spacing between extension and source and drain is nothing but your spacer, right? So by increasing, this is my spacer, you know how to fabricate, how to integrate this spacer in the flow. So by changing, this is actually s, right? So by changing the thickness of the spacer, that means by changing the thickness of the spacer, you could change the spacing between extension and source and drain, right? Okay, so if you go on reducing this junction depth, right? Let's say extension part, right? So if you go on reducing this extension depth or junction depth of extension, so your source and drain coupling will reduce. So your DIBL, charge sharing, everything will reduce, right? And you will have a better device, right? That's the reason. That's the motivation that people. Okay, so if you see with different technology nodes, if you go from one node to other node, your junction depth is scaled, right? Your junction depth reduces just to take care of the short channel effects, right? But here, if you think, like, let's say now, let's say I am giving some gate voltage, right? Your source, let's say source is at ground, and drain is at some voltage, let's say very low voltage around 50 millivolt, right? And your body is ground, right? And you give your gate voltage more than threshold voltage. If you give gate voltage more than threshold voltage, the electrons will be injected from source, right? So electrons will be injected, right? And the electrons will diffuse. I mean, not diffuse, sorry. Electrons will drift from source side to the drain side, right? And then they'll be collected at the drain, right? So if you look at drain, let's go to the drain part, right? So the moment, so basically I have just a moment. So I have an inversion layer here, right? I have an inversion layer. The electrons are coming from the inversion layer, so they are entering. So you see, so inversion layer has a finite thickness T inversion, right? So electrons are in the inversion layer and they're entering source, right? So when they enter from the inversion layer to the source, there is a thickness difference, right? So T inversion, they're flowing in T inversion, then they go to the XJ1, right? So this is the thickness of the inversion layer. Then when the electrons enter your source or drain, or let's say in this case drain, so they just go from T inversion to XJ1, right? Because this is also highly doped region, they go to XJ1. Then after XJ1, after then from the extension they go to source and drain. So they go from XJ1 to XJ2, right? So this is the thickness, right? Thickness of the regions, right? But also we discussed in the CMOS flow that we have a region which is silicided, right? So this region here. So this region is silicided, right? So we silicide this region just to have a better collection, because when the electrons will enter, right? So basically they will spread because they are going from T immersion to XJ1. So there will be some spreading, right? Some spreading of electrons, right? Then XJ1 to XJ2, there will be another spreading, right? So this is spreading. So spreading I have shown by this, right? So they will spread, right? Spread and they will be collected. But since source has silicide, so the electrons will not spread much. They will be collected by the silicide, and then they will go to drain, right? So this is how then the current is in this direction. Current is in the opposite direction, right? So if you look at the path, right? If you look at the path of electron flow, so I could divide into a couple of regions here. So you see again here you could see the electrons are entering from the coming from the immersion layer. They are spreading. Again they're spreading, and then again they're spreading, and then they're collected. Right here they're spreading, and again they're collected. Right. So if you look at so a path, so this has so basically then we have also resistances, right, because 11. So when you look at, so if you look at, uh, I have also finite resistances, right? So this resistance are divided into couple of, divided into three things. One is so basically I could so then source and drain has finite resistance. It will have finite resistance. So I have run it by RS and RD here, right? Um, okay. So this resistance are couple of things. So one is contact resistance, because if you see the electrons, contact resistance is this part, right? This resistance, right? The electrons are going from silicon to silicide, right? Silicon to silicide or silicon to metal, silicon to silicide or silicon to metal. So this is not, so this is going from one material to other material, right? So there will be an interface, there will be resistance, right? And that resistance I call it the contact resistance, right? So this is my this is the contact resistance, right? Means contact to, or you could write down the silicide to silicon interface, right? Interface resistance. There will be resistance of the interface. Okay. Again, I will have another extension resistance. So extension is this part, right? So this part, right? So this will also provide some resistance, right? And the spreading, right? So because the electrons is spreading, right? So it will spread, right? Because electrons are entering, it is spreading. So immersion layer to XJ, first extension they will spread. Extension to source, then electrons will again spread, right? And finally, there is a contact resistance also, because this is metal resistance, right? So, or you could write tungsten resistance, right? Because this part is your tungsten, so your contact plug. So by plug is connecting, your contact plug is connecting between silicide and metal one. So that will have a finite distance, even if this is metal, even if this is metal, right? This is tungsten, but it will have a finite resistance, right? Okay, so let's see those things. Okay, so now if you look at the first thing first, so let's look at the interface, silicide to silicon interface resistance side. So if you look at this, right? So let's say um, I'll put it in a different thing. So right, let's say I have silicon, I have this cobalt silicide here, and then I have tungsten here, right? So this is the interface, right? So the electrons are entering, right, so this cobalt silicide, right? So if you look at, right, so this silicon is n plus, so it has a work function. What is the work function? Work function will be electron affinity, will be, which is around 4.1 electron volt, because this is n plus. So your formula level is right at the conduction band. So your electron affinity will be around, your work function will be around 4.1 electron volt, which is equal to electron affinity. But when you talk about cobalt silicide here, cobalt silicide has a work function of 4.6 electron volt. These are mostly mid-gap materials. So tungsten, if you think of tungsten, tungsten also has a work function of around 4.4, 4.5 electron volt, right? So so now the electrons is going from a material which has a work function of 4.1 electron volt to 4.6 electron volt, right? So that means there will be some resistance. The electrons cannot easily go, right? Because they have two different work functions. So there will be some resistance, right? And that resistance is the interface resistance, right? So how do the electron go from silicon to cobalt silicide? So this actually, if I draw the band diagram, which I have drawn, so you see, I have drawn the band diagram. This part is your silicon, right? So this part is your silicon. This is N plus silicon, and this part is your cobalt silicide. As I told you, cobalt silicide has a band gap work function of 4.6 electron volt, and silicon has a 4.1 electron volt. So there will be a metal semiconductor junction, right? So your cobalt silicide is a refractory metal, so metal and semiconductor junction. And if you do the band diagram, it will look like this, right? Um, so actually the electrons, because see, if there is a two different work function material, so there will be a region which is depleted, right? Which is means there will be a barrier for the carrier injection, right? But since this is N plus highly doped, right? So your barrier thickness is very low. Barrier height is dependent on your work function, but barrier thickness, right? Thickness is this part here, this part here. So this is very thin because your silicon is heavily doped, so your depletion width will be very small, and electrons actually tunnel, right? So electrons actually tunnel through this barrier, right? And your resistivity that you're talking about, resistivity, how easily the current could tunnel through this interface, that depends on the tunneling probability. If the tunneling probability is high, that means your conductivity is more, your resistivity is less, right? So your resistivity, rho c, because if you want to find resistance, you need resistivity, right? Resistivity into length by area will be your resistance, right? So your resistivity rho c will be inversely proportional to the tunneling probability. And I will not talk about tunneling. You know about tunneling. Tunneling probability will depend on the effective mass. It will depend on the barrier height. It will depend on the doping, right? So I mean, will not go through this equation, but you could write this rho c resistivity as a function of your barrier height and doping, and this is a quantum mechanical thing, so your h will also come, a Planck's constant will also come into picture. So here you see the tunneling will be more if your wd will less, right? Wd will be less if nd is high, right? So basically um, so if your nd here, if nd is high, that means your resistivity will be low because your tunneling will be high, right? So you could relate this equation, right? So just keep in mind, this interface, right? So because we never think about, right? We think, okay, electrons are being collected, then they'll be taken by the contacts, right? But the contact to your semiconductor interface, it does matter, right? So if that interface is not very good, so then there will be a resistance to the means to the carrier flow, right? So the interface resistance will be high, right? Okay. So you could think of, right? Let's say your barrier height is very high, right? Let's say you have silicon, but you do not have cobalt silicide, some other material which have a very high work function or different work function. That means your barrier height will be changed, right? And similarly, if you don't dope it right properly, right? Let's say you know, instead of making it n plus, if you make n minus, right? Then also your resistivity will be high. So once you have this resistivity picture, then you could find your resistance, contact resistance. So your contact resistance is nothing but rho c into length and your area, right? And area is nothing but, if you see, area means current is flowing. So area is the area of this interface, right? Right. So area is the interface, and length is actually length of the interface, right? Length of the interface, right? And area of the interface, right? So you could calculate this contact resistance. All right. So this is where the contact resistance comes into picture. So this is one part of your resistance. So other part is the extension resistance, right? So basically, uh, your let's say in this case this is source side, so your current is entering, right? So if you look at this part here, right, this part, right, so this is a finite, this has a finite thickness and all those things. So this will be a sheet of semiconductor with some doping, right, n plus, right, let's say, right. So it will have a resistance which is extension resistance of the extension part, and I could row L is the length of the extension, which is S divided by xj times W. That is the area of this part, right? The wall, right? So xj, this is xj1, let's say xj1, then it will be xj1 times W. So since junction depths, we do not really, in the design manuals, you will not find the junction depth, right? Junction depth is very much technology dependent. So what you actually do is we take the xj1 out. So this row by xj1 here, this is called the seat resistance, right? So this is the seat resistance. So this is my seat resistance. So seat resistance into S by W is your total extension resistance, and your resistivity is nothing but your rho is right, so the resistivity is 1 by q mu nb, right, and your rho extension will be seat resistance, so your r extension will be seat resistance times s by w. So if s by w ratio is very high, then your extension resistance will be high, right. So see, uh, you could calculate extension resistance from the layout. So let's say you have done your layout, means if you have a layout, right? So um, right, and this is your gate, right, and right, you have spacer, right. So spacer, actually you don't draw it, but spacer will come right in the flow, right, in the right, and the spacer thickness is s, right. If you know s and if you know w, and if you know sheet resistance will be provided by the design manual. So if you know the sheet resistance, you could find the what is the R extension you are getting. R extension is nothing but rho extension, sheet resistance times S by W. All right. So this is um, the extension resistance. So there is another thing which will create problem is the spreading resistance, right? So basically, if you see, they have told you, so your electron, they are coming from T inversion, then they are spreading, right, from to T inversion to xj1, then from xj1 to xj2, they will also spread. So there are spreading resistance. So spreading resistance also there are formulas for spreading resistance, and you see the spreading resistance will depend on the this ratio, right? So if um, um, you see here, if xj equal to t, means if your this is just the relative ratio of two thicknesses, right? So it is like it will coming from t inversion to xj. So your spreading resistance will depend on xj into xj by t inversion. If xj is much higher than t inversion, that means it is spreading more, right? So spreading resistance will increase. Similarly, you have second spreading resistance because your electrons will go from extension to source and drain. So it will have this ratio xj2 by xj1 also, right? So total spreading resistance is spreading resistance 1 plus spreading resistance 2. So this is the modeling part, right? So this is how people model it, because many times you need to calculate this source and drain resistances, because I don't know how, means when you do the layout, we do parasitic extraction, right? See, these are all parasitics, right? Because we do not want this resistance. This is a parasitic resistance. The source and drain resistance is a parasitic resistance, right? We do not want this resistance, but this resistance has some effect on the circuit performance, right? We will see it now. Okay, so this is spreading resistance, and the next one is your contact resistance, right? Finally, the contact resistance, because you see, this is the your tungsten part, right? So the tungsten, because this has a finite resistance, right? Even if it's a metal always has a finite resistance. Metals do not have zero resistance, right? Right. So tungsten will have a final resistance. So basically, if you see, let's say I have my okay, let me go to here. Uh, so this is my silicide, right? And I have my metal here. Sorry, here my contact plug, and then I have my metal one here, right? Let's say this is a very thick. This is around, let's say, 1 micrometer, or let's say this is thickness of the plug, right? This is the thickness, right? So this has a finite resistance. So if I want to find the resistance of this contact plug, resistance offered by the contact plug, so this will be your rho resistivity, right? L is thickness, because your current is flowing from, electrons are flowing from this interface to the metal. So I am talking about this part. So this will be the thickness. This is the length of electron travel, T. And then the cross sectional area. Cross sectional area is width, because width of the because if you see means in the layout also, means I had shown you, right? The contacts are the contact blocks, right? And the area means, if you look at the design manual, so these are all square contacts, right? So this has a dimension. So this is W square, right? Width of the contact square, because width and length of the contacts are same, right? So this is the width square, right? So if you know, then you could find out. The only thing you want to know, because these are the dimension, you could always see. W you could always see on the layout, but the thickness, right? Thickness, you have to go and ask somebody like who does knows about technology, right? So you know, like this is the interlayer dielectric here. So what is the thickness of the interlayer dielectric? And what is the resistivity of the tungsten, you know, right? This is the resistivity of the tungsten. You could calculate this resistance of the contact plug. But if you look at the things, because we put a lot of contact plugs in, because contact because here you see I have two contact plug, because I have this, let's say this is my width, right? And this much width can allow two contact plugs, because the contact has a finite width also, and there should be a spacing between two contacts, right? I don't want contacts to be sorted, right? So design rule, if you go by design rule, so you'll have some spacing between two contacts. So you have multiple contacts, right? So if you see, if I take a cross section in this direction, so I have my silicide, because the surface is silicided. Then I have my metal one, right? And you see you have multiple contacts, right? You have multiple. In this case, we have two contacts. But if your width is high, you could put more number of contacts, right? So since there are contact plus coming in parallel, right? Contact plus coming in parallel. Actually, the resistance will be the parallel, means basically will reduce, because we have resistances in parallel, right? So the total resistance of the contact plug will is less, right? That's the reason we never, means we always assume that contact plugs do not offer much resistance, because we have a lot of these contacts in parallel, right? Right. So means I mean, when you're doing the layout, when you're designing a transistor, right, you should not actually put only one contact. One contact is always it's bad, right? So if your width is permitting, if the width is permitting, then put more number of contacts, right? See, single contact में एक problem है कि, because your electrons, see, if you see, your electrons are coming like this, right? So if they want to go here, then they so basically every electron will go to that contact, right? So path they travel. See, resistance is nothing but how much distance an electron is traveling, right? If there is one contact somewhere middle, and every electron will go to that contact, so they will travel more path. But if I have multiple contacts, right? Let's say I have multiple contacts here, right? I have two contacts or three contacts. Then half of the electrons will go to one contact, half of the electrons will go to other contact. So basically, your resistance will reduce, right? And also there is a risk also if you have a single contact. The risk is many times during processing, if there is a void, right? So let's say there is a void. Void means there is some contact is not properly filled, right? So you have contact plug, but the metal is not properly filled. When you're filling it tungsten, there is a void. If there is a void, this means that means it provides very high resistance. There is a possibility. Fabrication, during fabrication, there is a possibility of void, right? So If you have a single contact and let's say this single contact has a void, that means the resistance will be very high, right? And resistance is very high means your transistor may or may not work. So that's the reason, if possible, put more number of contacts. If one contact is not working, other contacts can take care of, means electrons can go through the other contacts, right? So your overall resistance can reduce, right? All right. So this is about resistance. So we saw that it's basically the summary of this discussion, that we have finite source and drain resistance. Source and drain resistance is not zero. So the source and resistance are finite, and they depend on junction depth. They depend on contact resistivity and everything, right? And basically, they depends on technology nodes, right? So now we know that, okay, we have this RS and RD. So if you see, you have your transistor, right? So and you have a source resistance and drain resistance. So and this is your external drain contact, and this is your internal drain contact, right? So this is your internal source contact, right? So if I'm applying VDS to the transistor, the actual I am applying VDS, right? If I'm applying VDS here, right? But actually VDS that you're getting is VDS dash, right? And your VDS dash is nothing but VDS minus ID times RD plus RS, right? So if you are, even if you are giving some voltage VDS, right? But what are the voltage? What actual voltage reaching the transistor is VDS minus ID into RD plus RS, right? If your resistances are very high, that means if you are giving 100 millivolt, you are thinking, okay, I am giving 100 millivolt here, right? Sorry, you are giving 100 millivolt VDS, but actually VDS that you're getting might be 50 millivolt, might be lower than 50 millivolt, depends on the what is the resistance, right? Right. So that means your transistor will not perform as it should perform, right? Okay, another thing, what about VGS dash, right? VGS dash, because VGS dash is the actual VGS that your transistor is getting. So this is nothing but VG minus IDRS, right? So even if you are applying some gate voltage, actual gate voltage reaching is VG minus IDRS, right? So basically what I'm telling here, because of source and drain resistance, actual VGS and actual VDS reaching your transistor is less than what is applied outside, right? So when I'm talking about ID, your current, let's say in one case in the linear region, your mu C ox WL VGS minus VTS, right, into VDS, right? Uh, this is your current in the linear region, right? Uh, right. But now actual current is mu C ox double by L. So your VGS is VG minus IDRS minus VTH, and your VDS will be VD minus ID times RD plus RS, right? Right. So you see, your current, because of the source and resistance, your current will reduce, right? So if you're expecting some current, because your resistance are not optimized, you will get lower current, right? So this is the issue in advanced technology in nodes. This is again a problem for very, means when you go to very scale transistor. When I talk about very scale transistor, so when you go to very scale transistor, you want to reduce the short channel effects. How do you reduce the short channel effects? You have to reduce the junction depths and all those things, right? But when you reduce the junction depths, your resistance increases, right? So these are the second order effects we usually see in advanced CMOS technologies, right? Right. And now, means when you let's say we have moved to FinFETs, right? We have moved to nanosheet FETs. FinFETs and nanosheet FETs, their thickness of silicon is very thin, right? Very thin silicon, right? When you have very thin silicon, you will have very high resistance. This is another issue in advanced transistors, right? This resistance, right? So uh, means actually this is the means actually there are a lot of effort, right? So means lot of efforts put to manage the resistances in advanced nodes, right? When we're talking about 7 nanometer node, 5 nanometer node, and 3 nanometer node, so lot of effort, actually huge research effort is put how to minimize the source and drain resistances so that you could get current. Because if the source and resistance is not properly optimized, right, so you lose a lot of current, because even if you're applying some voltage outside, that voltage is not reaching the transistor, right, and your current will reduce, right? And if your current will reduce, your speed will means everything will be affected. All right, so this is about source and resistance. I will not go further. You know how, means you could means you know how to calculate it, and what are the effects of source and then resistance on the transistor performance, right? Right. So if I draw, means so let's say if I have a IDVD curve, right? IDVDS. So if this is my IDVD, so this right, this is for a particular VGS, right? So you see, when you have finite, so let's say in this case your RD and RS equal to 0, right? But when your RD and RS is finite, that means your VGS will reduce, right? Your VGS will reduce, your VDS will reduce. So what you will get is you'll get something like this, right? Right. So that is with RD RS not equal to 0. So couple of things will happen, because your current will reduce, because your VGS has reduced, because VGS will be actual VGS will be VGS minus IDRS. So your VGS will reduce, and also your current will not saturate properly, right? So previously it was saturating at this point, because but now because your resistance, finite resistance, it will not saturate. It will saturate later, right? At a later point, right? So if it saturates at a later point, it will have some effect on the circuit performance, right? Because if you think about analog circuits, right? Analog circuits will operate always in the saturation, right? So if something is saturating later, that means we will have a lot of voltage drop across that resistance, right? Sorry, that transistor. So so these are the effects of source and resistance. That is a major issue in advanced technology nodes, right? When we're talking about nanosheet FETs, FinFETs, your resistance is a huge issue, right? And a lot of effort actually goes to minimize the resistance, right? Uh, and means basically, if you go to a foundry, if you look at the 5 nanometer, 3 nanometer, 7 nanometer technology development effort, you will see a lot of effort will be given, would have been given to minimizing the source and resistance. There are people working just to minimize, thinking of ways to minimize the source and resistance. All right. I don't have anything to speak about source and resistance. Okay, so now we have discussed means couple of short channel effects. I think I'll not do more. Anyway, this is the last class. I'll stop here. So as I told you in the beginning, if you think about transistor, you could easily have another course on transistor, right? Full course on transistors, right? So, whatever we have discussed in this course is more than enough for you to start working on something, right? Working on device and working on transistors. All right, so I'll stop here. So basically, let's last 15 minutes we could discuss about if you have any doubts, and if you have any questions, we could discuss.
Sir, sir,
Yes, Nissan.